24 webinar series, Water in a Frozen Arctic, Cross-Disciplinary Perspectives. For those who don't know, USAPECS is the national committee representing United States members of the Association of Polar Early Career Scientists, or APECS. APECS is the international and interdisciplinary organization for undergraduate and graduate students, postdoctoral researchers, early career faculty members, educators, and others with interests in polar regions in the wider cryosphere. The mission of USAPECS is to stimulate interdisciplinary and international research collaborations and develop effective future leaders in polar research, education, and outreach. Our actions and collaborations are focused on and informed by inclusion, diversity, equity, and accessibility IDEA principles. This includes advocating on behalf of our members in regards to pressing issues in polar research at a national and international level. Now, before we begin, we'd like to discuss our code of conduct for this meeting.
Okay, so the webinar code of conduct is as follows. USAPECS wants to create and foster a welcoming, safe, productive, and inclusive environment. All participants are asked to remain respectful of others' thoughts and opinions and keep an open mind throughout the meeting. If at any time you have any concerns, we encourage you to reach out to one of the meeting coordinators. Please type all questions or comments you have into the chat feature. Moderators will communicate them to the speaker after the presenters are finished speaking. We ask that you remain muted at all times to reduce background noise.
Okay, so without further ado, here's our topic for today. So heavy precipitation and other thawing events are increasing around the Arctic. Global climate models project that these extremes will only continue to increase in likelihood over the next few decades. The presentations today will feature different perspectives on the changing water cycle around the Arctic, with a focus on its causes, impacts, and implications on the wider region and the globe. So we're going to move on to our first group of speakers. So speaking group number 1, and I will stop sharing my screen.
Yes. So I guess I can start. Welcome, everyone. So I will be the first speaker. My name is Jorrit van der Schot. I'm a PhD candidate in snow climatology at the moment, based in Austria, University of Graz. And I'm presenting together with Sophie Elixhauser, who will do the second part of the presentation. Yeah, so I'll start right away. I will talk about rain and snow in Greenland, and also a little bit in Austria, but we're talking about polar things today, so we'll focus mainly on Greenland. And we will talk about the transdisciplinary research activities that we had for 2 research projects, one called Snow to Rain and one called Snow to School. Let's see if I can move on to the next slides. Yes, I can. So our story starts on the east coast of Greenland, which is where we did our research project Snow to Rain in a town called Tasiilaq. And this was a transdisciplinary project, and we will talk about that transdisciplinarity today. So what that means in the context of our project is that we integrated snow climatology and anthropology as 2 scientific disciplines, and also involved local expertise. So we were focused on exploring environmental changes in this region, and particularly focusing on the precipitation shift from snow to rain. So we know with Arctic climate change that we expect more rain in the future in the Arctic, as I think the other speakers will also speak about, so I will not mention further details here. But what we wanted to do is to place those changes in the context of people's lives in Tasiilaq, and also by doing this, explore the potential of combining these different lenses on one topic and see where that could lead to, and draw some lessons from that, which is what we will also share today. So very shortly, just some snippets of the fieldwork we conducted in Tasiilaq in East Greenland. You could see it as 3 fieldwork periods we had, where the first one, me and my former colleague, Anna Budensky, who was a PhD student for the project in anthropology, now no longer involved. But we really spent a lot of time, a month in Tasiilaq, to introduce ourselves first as persons there, and then also as researchers, and to share our research ideas and what we wanted to do there. And that was really valuable. Of course, it took a lot of time, but we needed that to build trust and to really get to build a mutual understanding in such a different place, of course. So one of the things we did in this first period is also installing a snow sensor to measure the snow conditions, and we could not also do this alone. So we also had local partners helping us out, for example, with electricity supply. And this was a difficult process, but very valuable. Second trip for the fieldwork was in the next summer, when we had a workshop sharing our intermediate project results, and also basically listening to residents of Tasiilaq what their concerns were related to our project topic. And they brought up a lot of things that we were not really familiar with. For example, the increase in earthquakes in Tasiilaq, and other environmental topics, like, for example, there's a strong wind called Pitarak. And they had a lot of questions about these things, and we wanted to answer them. So that's why in our last fieldwork period, which was spring last year, we had a science and climate exhibition in the local museum, where we shared some of our answers to the questions they posed during the workshop the year before. So what did we learn from that? I will very briefly share some outcomes. So we have one scientific outcome here, which we will submit very soon. And here we talk about the lessons we learned from this transdisciplinary process. Some of them I've already talked about. So we, of course, what we did was we integrated some local concerns into our project, but this, and we see that as partly a success, but also there are a lot of limitations since we had to do this on the go with not so much time and other priorities. And this is difficult to do when there is limited capacity in Tasiilaq. And it also leads to some unequal power relations, which is something we would like to change. So we argue that these sort of transdisciplinary research projects can greatly benefit from time investment before the project has actually started. So to talk about some shared interest to make sure that there's not only scientific relevance, but also local relevance. And these and also more issues are also talked about in the policy brief that I was lucky enough to be able to work on to the European Commission. So this is what you see on the right. And here I hand over to Sophie for the next parts.
Yeah, thank you, Jorrit. So my name is Sophie Elixhauser. I'm a senior researcher in social anthropology at the University of Vienna, based in southern Germany. I was also part of the Snow to Rain project with Jorrit, and we kind of applied for a sort of follow-up project, which is called Snow to School, right? Which kind of is building up on the lessons we learned from Snow to Rain. In Snow to School, we work in another region in Greenland, which is Uummannaq, and at the same time we work in a region in Austria, Eisenerz region. Snow to School is a transdisciplinary citizen science project, so it has kind of a similar setup than Snow to Rain. It's like some anthropologists, some climatologists, and also local partners. But the newer thing is that we use a citizen science approach, and we involve 2 schools, one in Uummannaq and one in Eisenerz, where we closely collaborate with students in the schools. So some words about the citizen science approach. Citizen science is attributed to 2 scientists and ornithologists, Rick Bonnier and a British sociologist, Alan Irwin, who coined the term in the 1990s. It involves like it's based on the premise of the involvement of the interested public in data collection and the possibility of large-scale and long-term research in science education on the one hand, and at the same time it forwards a call for a democratization of scientific knowledge by involving the society more deeply in a dialogue on goals and impacts of research. So in Snow to School, this means that we involve school students both in qualitative and quantitative snow research. We teach the students basic methods, basic research methods, for instance, to conduct snow measurements, manual and automatic measurements, to collect photographs featuring snow, because we are developing a method to reconstruct snow heights by means of old photographs. As for instance, in Greenland, there's not a very long time series available for snow data as compared to Austria, where there's a lot of data available. Then the students are going to do semi-structured interviews about past and present snow conditions and narratives, memories, and they will use photo elicitations to induce memories and narratives. So we are at the moment in the process of doing workshops, of kind of setting off this project in both regions. It has been running for 3/4 of a year. In the next month, the first Greenland field trip is coming up for me and another climatology colleague. And our anthropology colleague in Eisenerz has also been doing ethnographic fieldwork in the region and will do prolonged periods of fieldwork still. So next slide. So the project also includes this intercultural dimension of transdisciplinarity on the topic of snow in the environment. We bring those two schools together by means of an online exchange, which is facilitated by us, the academic project team, and also teachers from both schools who are also important actors in the project. So that's kind of this twofold dimension of citizen science and this intercultural transdisciplinarity. Yes, so this is kind of like just a brief introduction to the different approaches we've been working with recently. Our general take-home messages from this talk is that transdisciplinary projects can profit from the methods repertoire of both citizen science and also of a co-creative approach that Jorrit has mentioned before, which includes, which is based on the main message that it's important to include the non-academic partners throughout all the stages of a project, not only for data collection, but also when defining a project theme and then throughout the whole project. So a dialogue between academic and non-academic stakeholders, we argue, always involves mutual learning. So we always learn a lot from our collaboration with non-academic stakeholders, knowledge that we are not aware of. And at the same time, our partners learn a lot from the scientific information we bring in and other things. So as I've said before, we argue that it's crucial to involve non-academic stakeholders right from the start when developing a research project to ensure democratic procedures, to not perpetuate post-colonial power structures, and to increase the chances of a successful scientific project outcome. So thank you very much. We're open for questions, I think, later on. And here's some links where you can find us in the projects and talk later.
Okay, thank you very, very much for the wonderful talk. And just a reminder to everyone, if you have questions, please write them in the chat, and we will ask them to the speakers at the end of all 3 presentations. So moving on to our presentation number 2 from Michelle. So I will shut off my mic now.
Hopefully you can see my presentation. All okay? Yep. In a nod. Yes, so thanks for inviting me to come along today. Talk a little bit. I will apologize if there's a little bit of background noise. I'm actually currently in an airport, unfortunately. Just time zones were a bit, I got a little bit confused. Because as you can see, I'm at the University of Auckland, so I live here down here in New Zealand. But previous to that, I used to live in Canada and in the UK, originally from Ireland. But my research has been trying to understand change in precipitation across the Arctic. So I conducted this work looking at precipitation change, both using observations and model data. And it really started out with from a rain on snow project that I was involved in here, in Canada, when I used to work there as a postdoc. Trying to understand how in the new models, in the CMIP6 models, which are models that are used for IPCC, how things are going to change in the future. So it took me into this world of trying to understand how changes are happening. But we're able to see here, this is looking at some of the observed changes in Arctic precipitation. The models are showing, some old models, I should say, are showing that there is an increase in precipitation. However, if you look at this bottom panel, actual observations, so reanalysis data sets in particular, are showing that there isn't really any change in precipitation across the Arctic. This could be for a myriad of reasons, such as there are a lack of stations. The stations that we do have incomplete and inaccurate data. A lot of the times they will break down and they're quite difficult to get to, so live in the depths of winter. So I will caveat the start of this talk on that there is issues in how we get observations in Arctic precipitation. Move forward, yeah. So I've looked at it in terms of the model. So I did a comparison between CMIP5 and CMIP6 data. And we can see here that there is an increase in the CMIP model. So the yellow line is CMIP6 and the green line is CMIP5. And the ERA 5 is in between that. So it does sort of show in ERA 5 that there is a slight increase in precipitation that's in line with what the models are showing. So it gives you some confirmation models are actually showing similar to what the observations are showing. Other observations like the GPCP, which is the Global Precipitation Climatology Project, quite a mouthful to say, actually has inaccurate observations. And this is going back to what I was saying previously about some of the observations in the Arctic and precipitation still aren't amazing. The one thing that is really evident, however, is that we're seeing a reduction in the snowfall ratio. And what I mean by snowfall ratio is how much of the precipitation is falling in snowfall, or falling in rainfall. So I can see that going down in both the observations and in the model data. And it's actually evident as well in the observations. So this is a figure taken from a paper in 2020, where the top panel is looking at liquid precipitation and the bottom panel is solid precipitation. And you can see this is over Svalbard, where we can see that there is this increase in liquid precipitation since the 1980s. And that's simultaneous with a decrease in solid precipitation, so a decrease in snowfall layers. So what does it mean for the future? This is looking at SSD 585, so this is like the worst case scenario, you could say, but in all seasons, so I've broken it down for all seasons, that we're seeing this increase in precipitation throughout the entire century. This is dominated by increases in rainfall rather than snowfall, so that's the green line that you can see. What's most interesting in this project is that we found that the CMIP6 model, so CMIP6 is a project that happened in the last couple of years. We compare to CMIP5, which is the project that happened maybe 10, 12 years ago. So it's an updated sort of new improved models. What we're seeing in these newer models that there is this greater increase in precipitation and this greater increase in rainfall. So it's quite maybe difficult to see on screen, but we've the dark green line here, and then down here you can see a dashed light green line, and that's the same of 5. So you can see this big difference in the two model data sets. And finally, most of the changes that we're seeing are really happening in the autumn or fall period. I just wanted to show this as well. So this is looking at the different scenarios. So this is a SSB 245. So this is sort of a medium range scenario. But in that as well, we are still saying that there's going to be this increase in precipitation across all seasons. It's bigger than what we find in the SSB 585 and Arctic 8.5, but there still is that difference between the two model data sets. So that was looking at the Arctic wide, but what does it look like actually on the ground in terms of spatial precipitation change? So I've broken it up into winter and autumn changes, when most changes are happening, or most interest anyway. And we can see that, interestingly, there will still be snow at the end of the century. So this is looking at end of century change in CMIP6. So how things have changed by 2090, 2100 compared to current time, so 2005 to 2014, we take in difference in those. And we can see that by the end of the century, there still will be snowfall in the Arctic in winter. I think that is evident because so the polar nights, it's still cold enough for snow to actually fall. But what we do see is that there is going to be this greater increase in rainfall in CMF6 by the end of the century, which spans up into the Barents Sea and over in the Pacific side of the Arctic as well. What's interesting here is that we looked at the difference between CMF6 and CMF5, which is the difference in those two model data sets, and do find that there is across the entire Arctic, ocean, the significant increase in rainfall in wintertime over the Arctic. We also look at autumn period as well, so this is doing the same thing. So the panels on the left-hand side, hopefully you can see my arrow, are showing the changes at the end of the century in CMF6, and then this comparison between CMF5 and CMF6. And what's really interesting here is that the rainfall, we're seeing a drastic increase in rainfall in CMF6 by the end of the century, and that's coupled with this drastic increase in snowfall across the whole region. And again, in this comparison between CMF5 and CMF6, we can see that there is a significantly increased rainfall in the Arctic and significantly decreased snowfall in the Arctic with these new model data sets. The next thing we tried to do is to understand the drive resistance change. So we broke it down into three things that have been previously cited before. And what we have found is that we find, so this is looking at open water areas, so basically more sea ice or less sea ice, sorry, so more open water, that we find there's much more open water in the 6 models, so that there's greater capacity for evaporation and rainfall precipitation. So you can see here, for example, in wintertime, in these vial inputs, that's around that we expect by the end of the century, more open water, about 11 million square kilometers compared to only 6.57 in the CMF5 models, and that's seen across all seasons. We also find that CMF6 models are a lot warmer on average. Again, we can see compared here in wintertime that average temperatures by the end of the century should be around 15 degrees warmer in comparison to CMF5 models, which are about 11 degrees warmer. And what this means is that a warmer atmosphere can hold more water as water vapor. So therefore, again, a greater precipitation capacity in the Arctic. And finally, we've also found that there's going to be a greater increase in polar moisture flux into the Arctic in the CMF6 models. This is most evident in the summertime. So we can see here about an increase of, say, 13. This is looking at the vertically integrated moisture flux throughout the whole atmosphere. So if we're going to get more moisture into the Arctic, that also means more capacity for precipitation. And instead, this is most dominant in the summertime. The next thing we try to look at is, or understand, is how the Arctic is changing in the future and when that might actually be. We look at the fact, so when snowfall will from less dominant and will be more dominant. And you can see here, so blue means that by 2100 it's still snowfall dominated. But then going down in the colors shows when this transition might actually happen. So the lighter blue is 2090, 2080 in green, and so on and so forth. We can see in the wintertime and the springtime that it still will be snowfall dominated across much of the Arctic, but there are changes happening, especially in the Barents Sea area, which is where most of the warming in the Arctic is happening presently. The greatest changes, as I said, are happening really in the autumn time. So we look at this comparison between CMF5 and CMF6 as we've done previously. And we can see, you can look at the difference in this panel L, where there's much more blue. So that means that there's going to be an increase or a transition about 20 years earlier. So a 20-year difference on when there's going to be this transition from a snowfall-dominated precipitation to a rainfall-dominated precipitation. And this really also turns all the way into the Arctic Circle. Greenland is still mostly snowfall-dominated in the models, but in the Arctic Ocean, we're seeing the transition happening. And finally, on this work that I've done, because we are, in terms of policy, interested in what a 3-degree world will look like. She separated it out. We looked at the different regions across the Arctic, separated them out into different squares, as it were, and looked at when the snowfall ratios, when they're going to be change of snowfall. And we can see in a 3-degree world, so anything that's below the blue line shows like it's going to be a rainfall dominant 0.5, 50%. And a lot of the Arctic is going to transition at that point. But if we stay within this 1.5-degree world, we can see that all these regions to the left-hand side are showing that they are actually above the snowfall ratio, meaning that there's going to be, it's going to remain snowfall dominated. So it really is a call to action that we need to ensure that we stay within this 1.5-degree world. And the last thing I just want to kind of touch on about the impact of this change in precipitation are about the impacts. So it's some work that I have been working on in terms of the rain and snow events in particular. So if we've got more rainfall happening, and it kind of ties in quite nicely with the work that our previous speakers had talked about talking the changes in rain and snow. We actually look at the rain on snow event, so we find that that impacts reindeer and caribou. So you get these layers of ice through the rain, through the snowpack, sorry, which means that reindeer and caribou aren't able to pick their way through, so they actually have a lot of starvation and die-off events. If we have increased precipitation, we're going to have fresher oceans because of increased precipitation and river runoff, and that then can equate also to greater primary productivity through enhanced river nutrients. So these are just like 6 sort of main conclusions of the work that I've done and a little bit of like the impacts. I'll leave it here if anyone wants to read them, and thank you very much.
All right. Thank you so much for your presentation. I would ask that you stop sharing your screen. Perfect. And we will move on to our final presenter, Kristen.
Thank you. And just take me a minute to get this all going. Okay, I think we have it. Great. Thanks everyone for being here. My name is Kristen Poinar. I'm an assistant professor of geology at the University at Buffalo in New York, and I study the Greenland ice sheet. My team and I write simple models for specific processes that affect the ice sheet, and we apply them to the current ice sheet and to future versions of it. And today I want to share one very specific aspect of the ice sheet that we study, fern aquifers. You may not have heard of these before, but they are just like groundwater aquifers. So liquid water saturates a portion of the subsurface, which is under the subsaturated zone, or under the unsaturated zone. Except here, the substrate isn't rock, it's fern. Fern is an icy material that is midway on its journey from starting as snow and slowly densifying and compacting into glacier ice. So that fern has pore space, and liquid water can fill that pore space and become an aquifer. So the key to keeping that water liquid in the Arctic is the insulating properties of the snow above it. So the water table is about 20 meters down, and that 20 meters of snow above functions like an igloo, keeping the liquid water warm, 0 degrees Celsius, even when wintertime air temperatures above are -20 C or even -40 C sometimes. So we've traveled to a specific fern aquifer, and you would never know that there was liquid water under your feet. So we start in Tasiilaq, where Jorrit and Sophie have been talking about. We take a helicopter up onto this ice, onto the ice sheet at this site near Helheim Glacier. The conditions look like this. There's persistent 20-knot winds blowing snow, and sometimes bright sunny blue skies like this, sometimes clouds and more snow, even in June. So I would love to show you the subsurface conditions here, but I can't do that in Greenland. I have no footage. There is footage from Antarctica, so we need to take a very quick trip down south. So this is footage from the Ra-Badoine ice shelf in Antarctica. It was taken by my colleague Jan Leenerts when he was at the University of Colorado. Ra-Badoine, the ice shelf is named after a Belgian king, and that the research group likes to abbreviate it as the RBIS, the relatively boring ice shelf. And they went here to study surface mass balance, snowfall accumulation. It was a boring place where the snow layers should have been really easy to count. But when they took this core, they found all of this water in the snow layers, totally useless for learning about mass balance and snowfall. And they lower this camera into the borehole. 4 meters down, they come out into this totally liquid water lake. So this is something like an aquifer, but this is actually like a super aquifer because there's no fern down here. There's no substrate. There's only water. So this is kind of a more extreme version than what we have in Greenland, where there is fern and liquid water co-present. Okay, so back to Greenland. The colored dots show everywhere where fern aquifers have been detected here in Greenland, and they're color-coded by year, so 2010 through 2015, I think. The water that fills them is meltwater, which is formed in small quantities every summer, and it trickles down through the snow and fills these aquifers. So every year we have at least some melt, and it reaches these aquifers in the near subsurface. So if this were the whole story, then the aquifer water table would rise and rise and rise, maybe rise a lot in a high melt year and maybe rise only a little bit in a cool summer. And the water table would reach the ice sheet surface in a few decades. But this is not the case. So just like in a groundwater aquifer, the water actually flows laterally. There we go. And the specific discharge or the flow speed of the water through the aquifer is similar to a sandstone aquifer, a few centimeters per day. So it's slow, but it's actually pretty typical. So it slowly makes its way to these huge crevasses that sit at the downstream end of almost every fern aquifer that we've studied. And these are beasts of crevasses, 15 meters wide, some are wider. And they collect the water and they guide it straight down all the way to the ice sheet bed, which is about 1 kilometer below. And from there at the ice sheet bed, it has a clear path to the ocean where the aquifer water affects global sea levels just like any other meltwater that comes off of the ice sheets. Maybe you noticed in the previous slide that the fern aquifers sit in a small ring around a very specific part of the ice sheet, the south and the east. This is because they need specific climate conditions in order to survive. So first, they need to have meltwater to fill the aquifer with. Not too much, but some. They need at least half a millimeter. Sorry, I lost my pointer. Half a meter of water per year. So here's 500 millimeters. So we're looking at this orange zone. And second, they need lots of winter snow to form that igloo above to protect the liquid water. And we need 1 meter of snow water equivalent per year. So that's this line. And so we are describing this, this section of orange dots described in this paper by Max Brills et al. So we need 1 meter of SWE, which is the same as 100 centimeters of SWE on this graph. So you can see down here, 100 centimeters is kind of this light blue all the way up to purple. And greens and slaty blues don't count. That's not enough. That's not enough snow. The igloo's not big enough. So we're really looking at only this particular region of the ice sheet and a little bit up here in the northwest too, where we have enough snow to keep that melt water safe. And I can never help but notice that Iceland has enough snow for fern aquifers too. Southeast Iceland, the part that's most affected by the Icelandic low out here in the North Atlantic. So as the climate changes, we're getting more meltwater, that's obvious. And also possibly more snow, although maybe the previous talk makes me not think that. But anyway, the more meltwater suggests that the spatial footprint of fern aquifers should be growing. And the data says indeed that it is. So this study by Annika Horlings and co-authors measured 4 transects in Southeast Greenland that had fern aquifers and found them all to be expanding. So these aquifers are getting bigger, they're expanding further inland, higher onto the ice sheet. as the climate warms. So the data that this group used and the data that I'm also using for this talk came from NASA's mission Operation Icebridge, OIB, which flew from 2009 through 2019. It was a comprehensive, and that is an understatement, super involved airborne mission that flew over all parts of the Arctic. And as you can see in this map here, especially Greenland. It was usually flown on this P-3, a retired Navy plane, but they used different planes in different years as the conditions were needed. One important thing is that OIB flew every spring, March and April, which is before the melt season got started. And the OIB data allowed the detection of the aquifer water table all across Greenland. So the map that I showed you came from OIB. Here are the detections across a 14-kilometer reach in southeast Greenland. So just a little slice of where these aquifers are. And we have different years and different colors. So the water table is about 20 meters plus or minus below the surface. It varies from place to place. And it's about 20 to 30 meters thick. It's a little hard to see the year-to-year variation of the water table shown in the different colors here. So let's look at the same data a little bit differently. Now on the right axis, we're seeing the depth to water table. So shallow water table only 10 meters down, and it deepens down to up to 30 meters deep water table up here. So now we can see the water table rising and falling over the years, and even over just these 5 years, there's a lot of variation. Recall that these measurements are made in the springtime, March and April, so they really reflect the year before them, rather than the year that's shown. So spring 2013 followed the massive melt year of 2012, and we see that the water table in green is the highest, just what you would expect for immediately following the 2012 summer. So the data mostly bear that out. We would expect high melt years to lead to high water tables. So something like this, melt on the x-axis and depth of the water table on the y-axis, with shallow at the top and deep below. So something like this, a pretty tight correlation with inevitable noise here and there. Well, the data, what do the data say? They actually say something totally different. There is no such correlation, none at all. R squared equals 0.02. This is not good. But if you pay some attention to the colors, which again, they represent the years, and I've adjusted the years before so that the water table data observed in 2013, which is actually representative of the 2012 melt season, is here. So the highest melt year is 2012 colored, which is correct, but the highest water table is also 2012 colored, even though we observed it in the spring of 2013. So I'll do that for the rest of the talk. Minor thing if you're really paying attention, but otherwise no big deal. Okay, so look at the time pattern, follow the colors. And the correlation might not be so bad as it first appeared, since we can trace a pretty tame path from point to point in time. Okay, it's not a random chaotic path that crisscrosses itself and jumps from one side of the graph instantly to the other side. It's actually pretty smooth, even if it's not obviously predictable, but it does seem to have some memory in the system. So there's something here. I built a box model, also commonly called a reservoir model, which is a common way to study the water flow and the water balance in an aquifer. It looks like this. Here are all the fluxes. Water comes in from the top, it melts at the surface, percolates quickly through the unsaturated zone and enters the aquifer. And from there, it can discharge in two ways. It can freeze onto the ice sheet that's about 50 meters down from the surface, or it can discharge by flowing downstream and reaching the crevasses. And most of the discharge is through the crevasse, but the refreezing is not trivial either. We need to account for it. So if the influx exceeds the outflux, we should see the water table rise. And if the outflux exceeds the influx, we should see the water table fall. So this is a pretty simplified picture of how the aquifer works. It simplifies many specific processes that are complex, but it's a good first order picture of this system. So I took this model and I drove it with the actual melt rates from MERIT-2, which is NASA's reanalysis model that performs well over ice sheets. So this is the runoff. We see that the aquifer water mass, which is here in the red, this should correlate pretty well with the water table. We see the aquifer water mass rising and falling over time. So there's a short-term rise and fall with a 1-year period. And then there's also memory in the system sourced from high melt periods or low melt periods in the past. So we're just going to look at the red and the blue model output here, and it starts in 1980 and goes forward to 2023. And we can actually look at the effect of specific years. So 1986 and 1992 were low melt years, cool summers, and the aquifer barely gained any meltwater those summers while it continued to flow and discharge into the crevasses downstream, so it lost water overall. And we would see the water table come down in these years. And it actually stayed low for quite a while. As the water continued to flow out, it took a while for it to recover from the two cool years, even though the weather basically returned to normal immediately. So there's a lot of memory in this system. So conversely, in a warm summer with lots of melt, 2012, we see the water table rise. And again, we see the water table stay higher than normal, even beyond 2012, because of the persistence and the memory in this large aquifer system. So let's take these data and particularly, let's take these model output and particularly the aquifer water mass and zoom out on the years that OIB was flying, so 2007 through 2019. And we can compare the actual observations of the water table to the modeled aquifer mass. And this works a whole lot better, R² of 0.8. So the predictability is not perfect, but it's very good. This is a big improvement from R² of 0.02 when we didn't have the box model. So conclusion, this simple model added a lot of clarity to what was at first a surprising disarray where the observations didn't show at all what we expected. But then when you add a simple model that shows the basic processes of where this water is going, you get a much better correlation. And this apple is on the slide to remind me to tell you that this research came entirely out of a teaching demo that I made to show how to make a box model for one of my classes. So that's always pretty cool when your teaching time can align to the research that you're interested in. So overall conclusions, the Greenland fern aquifers deliver water to the bed where it affects global sea level. These fern aquifers are growing slowly over time, but there's a lot of internal variability as the water table rises and falls in response to large or small melt years. Until 2019, we were able to measure the water table every spring from NASA's Operation Icebridge mission. It stopped flying in 2020, although for Greenland, it really stopped in 2019 because in their last year, their closeout year, 2020, they only flew Alaska. So our data ends in 2019. And with the end of OIB, we're left with no way to directly measure where the water table is over large scales anymore. But the water table is predictable from the reanalysis data that give the melt rates. And it's not perfectly predictable, R² of 0.8, but it's okay. So all is not lost, even though at the end of OIB, we may never have continent scale observations of fern aquifer water table ever again. Okay, that's the end of my talk.
Okay, thank you so much for your wonderful talk and for all of our speakers.